Hi, welcome to lesson 3.15. We're going to begin graphing rational functions, and just as we've done with polynomial functions, we're going to use the key characteristics of these functions to sketch their graphs. Now, of course, they have x-intercepts and y-intercepts, just like polynomial functions, but they also have some rather unique characteristics as well that we've began to look at when we discussed the domain, and especially with our discussion about how concentration can never get over 100%. In the previous couple of days. And so today we're going to identify what are known as vertical asymptotes of rational functions, make sure we can find them, and what they mean about the function. So to get us started, go ahead and sketch the graphs of these functions along with the functions that go with them, algebraic representation. And your goal is to name 3 similarities between these functions. Don't worry about the graphs being very, very accurate. It's just important that you have the basic shape and just put the origin where it looks like the origin is. But you don't need to count things out, so on and so forth. All right, so hopefully that went well. If you found 3 similarities, or if you did not, you want to make sure that you write down the ones that we discuss here. So the first similarity, which is pretty obvious, is that both of these functions are rational functions. They both contain rational expressions. And with that, we know that rational expressions can have x values that make them undefined. And you can see here that when x is 3, this expression will be undefined. And the same is true here. When x is 3, 2 times 3 is 6, and 6 minus 6 is 0. So the function g of x will be undefined when x is equal to 3. And we can see that on the graphs of the functions, right? It's very clear that there is a place where the functions do not exist, where they cannot be. And they almost look as if they're, sort of an invisible line that we know is there, but that we can't see, because we know our function can never have an x value of 3. So we know that it'll never, ever be a point along this invisible vertical line. And these invisible vertical lines are what are called vertical asymptotes. And they're going to arise, of course, when we have a situation where there's an excluded value, where there's an x value that will make the denominator equal to 0 and therefore would cause division by 0. We can't define something when it's being divided by 0. Now, there are a couple of other similarities that are pretty obvious. Both these functions have x and y intercepts, right? Places where they intersect the x-axis and the y-axis. And we've found these before. We can find the x-intercepts by setting our function equal to 0 and solving, meaning that we just need our numerator to be equal to 0. So in this case, x would equal -1, be the x-intercept. And our y-intercepts can be found because that's just the y value when the x value is 0. But another similarity has to do with the vertical asymptotes, has to do with what these functions are acting like as they get closer and closer to that invisible vertical line. Well, you'll notice that this function, as we get closer to that vertical line from the left, appears to be getting very, very, very negative, maybe towards negative infinity. And here, this side, as we approach from the right side, the function is getting very, very large, maybe towards positive infinity. And the opposite is true here. As we approach that invisible line from the left, the function is getting incredibly positive. And as we approach from the right-hand side, it's getting very, very negative. So this is actually a tendency that occurs whenever there's a vertical asymptote. And so we want to test this out and make sure that we understand why this happens and how we can figure out which way it will go, towards negative infinity or positive infinity. So let's get rid of this function real quick and do a little bit of experimentation with f of x. Okay, so I've created this table. You want to create this table as well. And I've also drawn the invisible vertical line that our function can never touch with this blue dotted line here. What we want to do is investigate what the values of our function, our y values, are going to be as we get closer and closer to the place where our function is undefined, to x equals 3. So here's what you want to do. I'm going to put in an x value, 2.9. What I want you to do is use your calculator or Wolfram Alpha to compute the y value when x is 2.9. All right, so you'll see here that you get -39. Well, let's get even closer. Let's try 2.99. Try that one out. All right, here you're going to get -399. And I bet you can guess what will happen if you try 2.999. Yes, you will get negative 3,999. So I encourage you to try something with 4 or 5 nines just to prove to yourself that as you move closer and closer to 3 from the left side, your function is going to get massively negative. In fact, as negative as you want it to get, depending on how close you get to 3. All right, so now let's go from the right side. So let's start with 3.1. Try that out. You'll end up with a value of 41. Let's get even closer, and let's try 3.001. 3.001. You'll end up with 4,001. All right, let's go even closer, and let's try 3.0001. You're going to end up with 40,001. And let's just look at our function and investigate why this is happening. Because the x values were getting closer and closer to 3, our numerator was staying, well, pretty close to 4. But the denominators were getting smaller and smaller and smaller. As we approach from the left side, when we put in 2.9999, here we got a very small negative number. So we had some positive number divided by a small negative number, which gave us a very big negative number. As we approach from the right-hand side, and we plugged in values like 3.0001, our numerator again got closer to 4, but the denominator became smaller and smaller, but still positive, because this is slightly bigger than 3. And so we'd have a positive 4 being divided by a smaller and smaller positive number, which gave us bigger and bigger positive numbers. So we can decide whether it's going to approach positive infinity or negative infinity simply by looking at the sign. What is the sign of our expression going to be just to the left of 3? It's going to be negative. And what about just to the right of 3? It's going to be a positive over a positive, so it will be positive. All right, so now that we've sort of discussed vertical asymptotes, one last thing to mention is, how would you tell someone where this invisible line is? Well, you'd want to tell them how they could find this invisible line. And this is the line that goes through x equals 3, since x equals 3 is where it's undefined. And so you would say that the vertical asymptote is x equals 3, which is this straight line that we've drawn here. All right, let's go ahead and capture some of these definitions and things that we've talked about in our notes. Okay, so here's what a vertical asymptote is. A vertical asymptote is an invisible vertical line that we can write as x equals a. That's meaning it'll be through that point x equals a, so it'll be vertical, for some number a, which indicates a place where the function is discontinuous. And we've talked about this before. It's undefined at that point, and so it can never cross that line. These vertical asymptotes occur because the function is undefined at that x value. This is why we exclude that particular x value from the domain, because of the division by 0. So this really tells us how to actually find the vertical asymptotes. In order to find them, we just need to know where this undefined x value is. So we can do so by setting the denominator equal to 0 and solving. And whatever value we get, that's going to be the value a that we'll use to determine our vertical asymptote. So you might want to mention here that this allows you to find the a value in x equals a, the vertical asymptote right there. All right, what we also saw is that as the x values get closer and closer to a vertical asymptote from either side, the y values will approach either positive or negative infinity, right? We saw either go up or down. And we can determine which one by considering the sign of the function to the left and to the right of the vertical asymptote. So I just went through that exercise where we looked at that table of values, and so you can clearly check which way it will be going, towards positive infinity or towards negative infinity. And now let me mention one way that we can write this. So what you can say is, let's say that our vertical asymptote was at x equals a. So one way that we can say what it's doing as we approach this is we can say that f of x, our function, or the y values of our function, approach either positive or negative infinity, so you'd pick one, as x approaches a. But you want to be careful. You want to say which side you're approaching your vertical asymptote from. So if you're approaching from the left, you'd use a negative sign. And if you're approaching from the right, you'd use a positive sign, a plus sign. So we'll use this every once in a while, but it's very common in calculus to use this notation to tell you something about how your function is behaving as you're approaching a particular x value. Okay, let's go ahead and start applying some of this to our work with rational expressions. All right, so let's go ahead and take a look at these problems here. What we want to do is find the x-intercepts, the y-intercept, and the vertical asymptotes of each of these functions graphically. So let's go through the first one together, and then you try the second one on your own. So first I'm going to look for the x-intercepts, and of course we know that to be where it intersects the x-axis, and we can see that that happens here at x equals 2. So the point where that is occurring is when x is equal to 2 and that y value is equal to 0. And what about the y-intercept? Well, the point where it intersects the y-axis has an x value of 0, obviously, and a y value of -4. All right, now what about the vertical asymptote? Well, we can pretty clearly see that our graph is not going to cross this vertical line here, which seems to be passing through x equals -2, meaning we can never have an x value of -2. And so our vertical asymptote, that invisible line, is going to be the line that goes through x equals -2. So we can define it as all points that have an x value of -2, x equals -2. And you can see that in the algebraic construction here. Clearly I'm going to have division by 0 when x equals -2. All right, go ahead and try the second one on your own, and I'll post the solutions so that you can check them. Then we'll go ahead and try and do similar operations, but we'll do them algebraically. Okay, here are these solutions. Again, I'm just using the graph to make these, so you may have counted a little differently, but if you look very carefully at the way that we're counting, each tick mark represents 2. So this would be my x-intercept, my y-intercept, notice it's 0.6, and my vertical asymptote, which I can corroborate by looking at the function itself. I can see that 5 is clearly the value that will make my function undefined. All right, now let's go ahead and try doing the same thing, but algebraically. So we actually aren't looking at the graph now. We're just given the function. Let's do the first one together here. So I want to find the x-intercepts, which means I'm looking for where the y value is equal to 0. So I'm going to set my function equal to 0 and solve. Now notice that when I do so, I end up with a rational expression set equal to 0. Well, a fraction will be equal to 0 only when the numerator is equal to 0. In other words, I can multiply by the denominator on both sides, and this will still be 0, so I'll have x minus 4 equals 0, and that means x will be equal to 4. All right, so I know that the x-intercept is going to occur at 4, 0. All right, now the y-intercept. I know the y-intercept is just the value of my function when x equals 0. In other words, whatever f of 0 is. And so this will simply be 0 minus 4 over 0 minus 4. And that's -4 over -4, which is positive 1. So my y-intercept is the point 0, 1. All right. Now we want to find the vertical asymptote algebraically. And remember, this involves looking for where the denominator is equal to 0. So if you look back to your key points, what we're going to do is we're going to set the denominator equal to 0. So 2x minus 4 equals 0. And when we solve for x, we'll add 4 to both sides and divide by 2, and that will tell me that x must be equal to 2. So this is the value, my x value, which would make my function undefined, and that's going to be the vertical asymptote. So in fact, this is the equation for the vertical asymptote. This is a line that goes straight through the x value, positive 2. All right, go ahead and try the last one on your own. I'll post the solution so that you can check your work, and we'll talk a little bit about it in class tomorrow. All right, here are the solutions to check your work. One thing to note is what you'll see, there are two vertical asymptotes here. Remember, I never said there had to be one. There's no reason there can only be one. We've seen rational functions that have more than one x value, which would make my denominator 0, and therefore make my function undefined.